Okay, so in part two of our discussion on the properties of logarithms, most of this is going to be a review from part one, but there are some properties that I want to go back and discuss and kind of formalize a little bit better. All right, so as a review, so the first part is going to be a review. Now, before we do that, let's remind ourselves about the fact that logarithms and exponentials are inverses of each other. And we saw from part one that the this log function, this log equation, y equals log of x base b. And remember how we wrote this. Make sure this base looks like a subscript. Is equivalent. Is equivalent. So we saw that in part one. Is equivalent to, and remember how to change a log equation to, or a log form to exponential form. And so basically you take your base first, which is b, and you raise it to this power, so this is going to be your exponent. So I'm going to say b to the y power is equal to, and the argument here becomes on this side, okay? All right, now part of that definition, and so notice that when we use that definition, we went from, in part one, we went from log form to exponential, and we went from exponential to log. And again, part of what we're going to do today will be a review of that. But I want to go back a little bit further and mention that when we looked at the definition of, I'm going to write it as definition of the log function. Okay, so we looked at the definition of the log function. We said that this was equivalent to this for x being positive, so x had to be positive. And we saw that the base had to be positive, and the base could not equal 1. Now this part came from our study on exponential functions. All right, so that came from, and I think it was section 4.1. All right, so that was on exponential functions. So we saw that the base had to be positive, and the base could not be 1. All right, so exponential functions. Now, before we go on, I want to talk about this part though. So this kind of makes sense that the log, this argument, has to be positive, because I want you to think of this. When we looked at exponential functions, and let me look at a few problems that we did. So for example, when we did, and this came from exponential functions on part 3, so you may need to go back to that lesson. But look at the base. The base was positive, right? And so we said that the base has to be positive and the base cannot equal 1. But if you look at all of them, and we did the graphs, but if you look at all of them, so that was number 1. Here was, let's see if I can get the others. Okay, here's another one. So if you look at number 2, we saw that the base is positive. Okay. So when we did the lesson of exponential functions, the base had to be positive and it was not equal to 1, and we saw y was not equal to 1. Okay, now let's go back over here. The reason that x has to be positive, so if you look at this, basically you're saying you can only take the log of a positive number, and that's true. You can only take the log of a positive number. You can never take the log of a negative number, and we'll see some examples later on, but you can only take the log of a positive number, and it kind of makes sense from this part. So remember, the base has to be positive, right? And a positive number raised to any power is always what kind of number? A positive number raised to any power, any exponent, is always what kind of number? So if you go back to our example, the first one we did when we graphed this, so you see the base is positive? So my y value, so a positive number raised to any power, what was that y value? It was what kind of number? Regardless of what x is, regardless of what your exponent is, whether it's 0, positive, or negative, your y value is always a positive number. So that's why this says that this value here, x, must be positive. Okay? All right, and you're going to see that the log, when you take the log of some value, that right here has to always be a positive number. Okay? It won't be negative, and it cannot be 0 either. It must be positive. All right, so you're going to see this in a future lesson. Okay, now let's go back to this. All right, so one of the things, so this next part is going to be a review from part 1. So one of the things you did in part 1 was this. So example, so let's suppose you want to write each equation in its equivalent, right, in its equivalent exponential form. Okay? All right, so you're going to write each equation in its equivalent exponential form. All right, so number 1. So let's suppose we had log of x base 5 is equal to 6. Now again, if this was lined paper, we talked about this in part 1. If this was lined paper, log x equals 6 must be on that same line, and the base must be listed as a subscript. Okay? All right, so you're given this log equation, and you want to write it to exponential form. All right, so we're going to use our equivalence right here. So to go from a log equation to exponential, I have to first of all look at my base. So what's the base? The base is 5, so it has to have an exponent. What's that exponent? See how I'm kind of doing this here? So its exponent is what? 6. So I'm going to say, I'm going to say 5 to the 6 equal, and it's going to equal x. Okay? So you kind of go base to this exponent equals x. See, base to the exponent equals x. Okay? All right, number 2. So let's suppose we had 6 equals log of 28 base b. Okay, that's a b right here. That's 6. So again, I want to change this to exponential. So you look at the base first. So the base is b. So look at our arrow. So you say the base raised to the exponent, so b to the 6 equal 28. Okay? All right. Then the other thing we looked at, the other example we looked at was this. So in another example, in part 1, we wrote, so write each equation in its equivalent logarithmic form. All right. So now I'm going to go this way. Oops, this way. All right. Okay, so number 3, let's suppose we had 2 to the 8th is equal to 256. All right. And that's a true statement. If you take your calculator and do 2 to the 8th, you're going to get 256. But I want to write this as a log equation. All right, so the answer. All right, so you're going to say equal log. That's the way I would write this. I would put that first. Now the log has to have a base. That base is the same as this base. So that's going to be 2, right? Now let's use our arrow idea. So 2, see how this says 2 to the 8th? So 2 to the what? What goes here? 8, right? 2 to the 8, and the argument's going to be this right here. Okay? All right. So that was number 3. Number 4, you have 6 to the x equal 29. All right, no big deal. We can handle that. I say equal log. Always do that first. A log equation has to have a base. The base here is this base. So I'm going to write it as a subscript, okay? And so just like our arrows, we said 6 to the, look at my pencil, 6 to the x is equal to 29, so 29 is my argument, okay? Number 5, we have y equals 3 to the 5th. All right, no big deal, I can handle that. So I want to change that to to a log equation. So I say equal log. So the log equation has to have a base. The base is this base, that's 3. So write as a subscript. So we say 3 to my exponent's 5. So 3 to the 5th equals, and y, so y goes here. Okay? Number 6. All right, number 6, we have the 5th root of 1024 is equal to 4. All right, now, you got to remember something from a previous course when you dealt with rational exponents. All right, so remember the 5th root of 1024 from a previous course, you need to write this as a rational exponent. Write as a rational exponent. Write the radical as a rational exponent. So that was from 2 courses ago. And so basically you're saying the 5th root of 1024 means the same thing as 1024 raised to the 1/5 power. That's what that is. So this and this are the same thing. So remember in a previous course, this property, if I have a to the 1 divided by b, all right, 1 divided by b, that's going to equal the b root of a. That's what that is. Okay? So we saw that 64 to the 1/2, 64 to the 1/2 means the square root of 64, right? Which is 8. And you can look at your calculator real quick to see what 64 to 1/2 is. Watch. Watch, you're going to say this. You're going to say, watch your calculator, you're going to say 64 raised to the, in parentheses, 1 divided by 2. See that? 64 to the 1/2, right? Equal, what'd you get? 8. That's what we said this was. So that was from a previous course. So that was something you've learned a while back. Okay, so you had to rewrite this like this, and so that equals 4. All right, now I'm going to take this right here. I'm going to change it to a log equation. All right, so I'm going to say equal log. That base is this base here. So what's this base? 1024. So you can write that as a subscript, just like that. So 1024 raised to what power? 1/5. That goes here. Okay? And the 4 is my argument. And that's how it looks. All right? Okay, so that's number 6. Then the other thing you did in part 1 was without using a calculator now, without using a calculator. Okay, so no calculator. No calculator. Calculator. All right. So find the exact value. Find the exact value of the following. Without using a calculator. All right. Okay, number 1. Log of 8 base 2. All right, so basically, you want to find out what this is equal to. All right, so you have this, you'll be given like this, and then your goal is to figure out what the log of 8 base 2 is. That's your goal. Okay, you want to figure out what that is. All right. Now, without using a calculator, you want to make sure that you're using your property right here, this equivalent statement. The log equation is equivalent to this exponential equation. Okay? All right, listen carefully. So in doing these, see how it's not written as an equation? This was. See that you had an equal sign, right? Okay? Well, go ahead and make an equal sign. So that's why I did this little box. So it's always a good idea, if you're trying to find out what that's equal to, say equal box. All right? Now, here's what I would do. I would take this right here, and I would change this to exponential form. So since this is written in as a log equation, I'm going to write this as an exponential. So you're going to say 2 to the box equals 8. And now you can tell me what goes inside the box. 2 to what power is 8? 2 to what power is 8? 3. So that goes here. All right, so the answer here is 3. So the log of 8 base 2 is 3. Now, at some point in a future lesson, you're going to see how to use your calculator to figure this thing out. All right, number 2. Suppose we had log of 7 base 7. Log of 7 base 7. All right, well, without using a calculator, and you really don't know how to use your calculator with this anyway, so I'm going to go ahead and change this to a log equation. So I'm going to say log of 7 base 7 equals box. Now let's change this to exponential. Change to exponential. All right, so the same thing we do here. Change to exponential. All right, so you're going to say the base is 7, so 7 to the box equals 7. Now think, 7 to what power is 7? 7 to what power is itself? It's 1, right? So this is 1. So 7, the log of 7 base 7 is 1. Number 3, suppose we had the log of 1 base 11. Log of 1 base 11. All right, that looks hard, doesn't it? It really isn't. Let's think about it. So I'm going to do the same thing here. All right, I'm going to do the same thing here. I'm going to rewrite this as an equation. So I'm going to say log of 1 base 11 equals box. Now let's change this to exponential. Change it to an exponential equation. So I'm going to say 11 to the box equals 1. All right, now you got to remember some things. 11 to what power is 1? 11 to what power is 1? All right, remember from previous courses, we even had it in this course. 11 to the 0 power is 1. So the answer is 0. Okay, number 4. Suppose we had the log of the square root of 5 base 5. Log of the square root of 5 base 5. Well, that doesn't look good, does it? Well, you got to remember something we had a while ago. We saw right here how to write a radical with a rational exponent. So we went from a radical form to rational exponent form. So that fifth root means an exponent of 1/5. Okay? Notice I said fifth root, 1/5. So this is square root, right? So that means the same thing as this. So that means log of 5. Now what's going to be my rational exponent? We're doing square root. Remember that index here is understood to be a 2. So that's 1/2 base 5. All right? And so therefore, I'm going to go back. I'm going to change that to what we've been doing here with that box. So I'm going to say log of 5 to the 1/2 power base 5 equals box. I'm going to say this. The base is 5. The base is 5. So 5 to the box equals, remember how we did this, 11 to the box equals 1, right? Whatever I was taking the log of. What are you taking the log of here? 5 to the 1/2. All right, now look, if the bases are the same, let's think about this. All right, think. If I have 2 to the 3rd power, and over here I have 2 to the x power, and I want those two things to be equal, what must x equal then? If the left side's 2 to the 3rd, then the right side better also be what? 2 to what power? The 3rd. So the exponents have to be equal. So that means that the box has to equal what? 1/2. So 1/2 goes here. So it's equal to 1/2. All right, number 5. Suppose I had log of 4 to the 6th power base 4. All right, it kind of looks like this one, doesn't it? So I'm going to rewrite it. I'm going to say log of 4 to the 6th base 4 equals box. So I'm going to say the base raised to that box equals the log, what I'm taking the log of, I'm taking the log of 4 to the 6th power. And so again, if the bases are the same, then the exponents have to be equal. Same thing here. If the left side's 2 to the 3rd, then the right side better also be 2 to the 3rd. So x must equal 3. So the box must equal 6. All right, number 6. Suppose we had log of 1 divided by 16 base 4. Log of 1 divided by 16 base 4. All right, now that one again is a little bit challenging. But let's think about this. All right, I'm going to go ahead right now, and I'm going to, for the most part, I'm going to change it to this equation, and then I'll come back and have a little discussion. So I'm going to rewrite this as log of 1 divided by 16 base 4, right? Equals box. Y'all agree? All right. So I'm going to say 4 to the box equals 1 divided by 16. Now, I want to somehow use this idea here. I want to somehow use that idea that when the bases are the same, the exponents have to equal. When the bases are the same, so if I have b to the x equal b to the, let's say, a power, then x must equal a. The exponents have to equal. Okay? I want to use that idea. But this is a 4 and this is 1 over 16. But I want you to think about this. Isn't 16 4 squared? Isn't 16 4 squared? So that becomes 4 to the box equals 1 divided by 4 squared. And in a previous course, you saw this, that when you have 1 divided by a to the b power, that's the same thing as a to the negative b power. So 1 divided by a to the b power is the same thing as saying a to the negative b power, meaning this. So let's think about this. This was a previous course. There was a whole section on that. So for example, previous course. If I have 1 divided by, let's say, 9, okay? 1 divided by 9. Based on what I just said, I can rewrite this as 1 over 3 squared. Y'all agree? Because 9 is 3 squared. So do y'all agree that those two equal, right? All right. And based on this property, that negative exponent rule, I'm going to change this to a negative exponent. So it's a positive exponent in the denominator. So I'm going to take this and rewrite it. I'm going to rewrite the numerator the denominator, the numerator. So that becomes 3 to the negative second. Now use your calculator. Let's check it. 3 to the negative second. What shows up? 3 raised to the negative second power equals. All right, so remember this, 0.11111. Now let's go back here, 1 over 9. 1 divided by 9, what you'll get? Same thing, right? Okay, so just remember this. If I have 1 divided by, let's say, 36, do y'all agree that's 1 over 6 squared? Which becomes 6 to what power? Negative 2. That's what that is. All right, if I have 1 over 27, y'all agree that's 1 over 3 cubed, which is 3 to what power? Negative 3. Okay? Now, you went a little bit further with that. Do you remember also if I have 1 over, let's say, 4 to the negative 6 power, then that would be 4 to what power? So whenever you go from denominator to numerator or numerator to denominator, the sign of the exponent changes. So it becomes 4 to the 6. And it kind of makes sense because watch, I'm going to do 4 to the 6. Watch, 4 to the 6. So 4 raised to the 6, you get 4,096. Let's go and do this one. 1 divided by 4 to the negative 6, 4,096. Okay? All right, so that was something you learned in the previous course. We needed it here. We needed that idea. We needed this idea, the negative exponent rule, here. All right, so I'm going to go back and fix this. So this right here becomes 4 to what power? Negative 2. So now I have 4 to the box equals 4 to negative 2. So what does the box equal? Negative 2. So that becomes negative 2 right here. And so what does this equal? Negative 2. Okay? That was a little challenging. You may have to go back and review some things about negative exponents from a previous topic in a previous course. All right, now let's look at number 7. And I'm going to go ahead and do number 7 here. All right, number 7. So in number 7, let's suppose we had this. Log of 36, log of 6 base 36. Log of 6 base 36. Oh, that doesn't look too good either, right? That didn't look good. Because I know you can do this. If I have log of 36 base 6, y'all know what that is. Real easy. You can tell me 6 to what power is 36? Yeah, 2. 6 squared is 36. But that's not what that is. So let's rewrite it. So log of 6 base 36 equals box. So 36 to the box, 36 to what power equals 6. All right, well, let's think about that. You know that if I keep saying 36 to the first, that's not 6, right? 36 to the second, obviously that's not 6. So you know that this cannot be a whole number, right? So now you got to think then, well, then could it be a rational exponent? Yes, that's what it is. Do y'all agree? Do y'all agree that I can go from 36 to 6 by taking the square root of 36? And then how can I write the square root of 36 from what we did earlier? I can write the square root of 36 as a rational exponent. That's 36 to what power? 1/2. And so 36 to the 1/2 equals 6. So that's what that box is, 1/2. So that's going to be 1/2. That one was challenging as well. All right, that one was difficult. All right, number 9. Suppose we had this in number 9. Suppose we had 7 log of x base 7. Huh. Now, that's like, what did you just write? All right, well, that's doable. We can handle that. So I'm going to rewrite this. Now, I want you to notice, see how in 1 through 8 you started out with the log equation, right? Okay, now notice though this right here is, think of this as exponential, because you have that exponent here. So think of this as exponential. Think of this as exponential equation. So I want to change it to a log equation. All right, so I'm going to say equal log. Okay, the base here is this base. So what's that base? 7. So you said 7 to what exponent? So the exponent goes here. What's the exponent you see? This is your exponent you see. So you can say log of x base 7. And then the argument here is, oh, I forgot to put a box here. The argument here is equal to that box. So that's going to be box right here. Okay? All right, so you're going to change this log. You're going to change this exponential equation. I forgot to write the equation. All right, to a log equation. All right, now notice, I want you to think of this. Think of this. If I have the log of, let's say, 4 base 3 equals log of box base 3, and if I want those two sides to be equal to each other, notice the base is the same, right? Then the arguments have to be what? The same. So that argument's 4, then this needs to be what? 4. So that argument is x, then this needs to be what? X. So therefore, based on what we just did, that has to be x, right? So therefore, 7 raised to the log of x base 7 has to be x. One of the things I want you to recognize is this. This is important. Whenever you have a base raised to an exponent and that exponent contains a log, and those bases are the same, then your answer is just the argument. Okay? So in other words, let's think about this. If I have 8 raised to the log of let's say 6 base 8, what does that equal to? The base is the same, this base and this base are the same, so what's the answer? The answer is, let me go ahead and rewrite this. The answer is the argument, 6. Okay? So that brings us to a couple of properties we want to talk about. All right, so listen carefully. A couple of properties that we need to review ourselves or remind ourselves about based on what we just did. Okay, so the first one is going to be called basic logarithmic properties. Basic logarithmic properties involving the number 1. okay, involving the number 1. All right, so number 1, log of b base b. So if the argument and the base are the same, so let's go back to one of the problems we did. Find it real quick, right here. So remember a while ago for this one, the argument and the base are the same. What was that equal to? 1. So if the argument, listen to the words, if the argument and the base are the same, that is just equal to 1. Okay? Because b to the first power equals b. All right? So because b to the exponent 1 is b. Okay? Number 2. So again, involving 1. Number 2. What do you think this is? Log of 1 base b. What do you think that's equal to? What'd y'all say? Think. We had a problem like this that we did. What do y'all think? It is 0. It is 0, right? B, because b to the 0 equals what? 1. That's why, because b to the 0 is 1. So whenever, regardless of the base, as long as the base is positive and not equal to 1, whatever the argument is, this could have been log of, let's say, 8 base b. What's that equal to? 0. I'm sorry, 1. Excuse me. Let me do this over. Log of 1 base 6. What's that equal to? That's what I meant. 0, right? Because 6 to the 0 is 1. Log of 1 base 15. What's that equal to? 0, because 15 to the 0 is 1, right? All right, so obviously that what I did earlier was incorrect, because the base raised to some power equal 8, that's not going to be 0, because b to the 0 is 1. All right, so as long as the argument's 1, what's that equal to? 0. That's what that says. All right, and then I want to talk about the inverse properties. So there's something called the inverse properties. Of logarithms. And we talked about that already. I'm going to go back and show you. So if I have the log of b to the x and my base is b. If I have the log of b to the x and the base is b. So let's go ahead and find where we saw this. So this was right here. So when we said the log of 4 to the 6th power, see how that base, and I'm sorry, the base of the argument, here's my argument, the base of the argument and this base are the same, then the answer is just the exponent, right? So that's just going to be what? X. As long as the base of the argument and the base of the logarithm are the same, it's just the exponent. So in other words, if I have the log of let's say 7 to the x power base 7, what's that equal to? Here's my argument. The base of the argument is the same as the base of the logarithm, so it's just the exponent. Kind of makes sense, right? Because 7 to the x power equals what? 7 to the x. This is true since if I convert that back to exponential, because 7 to the x equals 7 to the x. All right? The exponents have to equal. Okay? So that's number 1. And then number 2 goes with this one. I want to remind you. Remember number 9 where we had that the exponent contained the log, the word log? All right, and notice that these bases are the same. The base of the exponential is the same as the base of the logarithm. And so the answer is just the argument. Okay? So this is what the second property says. That if you have b, and my exponent is log of x base b, so the base is the same, then that should equal the argument. That should equal x. Okay? All right. So again, if I have, based on this one, if I have 9 raised to the log of, let's say, 7 base 9. Real quickly, what's that equal to? The bases are the same, so it's just what? 7. That's what that says. Okay? All right. So that was a, in part 2, most of what we did was reviewed part 1. And then the new part were these properties right here that we had to discuss a little bit further. Okay? All right. So that's going to take care of part 2.